Every time you unlock your smartphone in a tech hub like Penang or track your heart rate on a wearable device, you are relying on two completely different worlds of engineering working in tandem. We usually refer to these items as digital devices, and we tend to assume everything inside them operates strictly through the cold, hard logic of computer code. But the real world is messy. The physical phenomena these devices track, things like the sound of your voice or the temperature of the air, exist as continuous, fluctuating waves of energy. This creates a disconnect. The processors powering your device only understand discrete, perfectly distinct binary states, simple ones and zeros. So how does a computer chip that only processes strict logic manage to interpret an infinite, constantly changing physical environment? On its own, a purely digital processor has no way to perceive reality. It needs a specialized engineering bridge to translate the physical world into a language it can process. The first point of contact for a real-world signal, like the pulse of a heartbeat, is an analog circuit. Think of these as the listeners, designed to capture raw physical energy. Because nature is unpredictable, analog design requires precise tuning at the transistor level. Engineers must account for environmental noise and extremely subtle variations to ensure the signal is captured accurately. Once captured, the physical wave reaches a bridge, the analog-to-digital converter, or ADC. The ADC slices the continuous analog curve into distinct, rigid intervals. What emerges is pure binary data, a stream of ones and zeros the processor expects. Without this translation, the raw data of the natural world would remain entirely invisible to the computer's brain. With the data successfully translated, the digital integrated circuits take over. These are the thinkers, operating entirely on logic abstraction. By leaving the messy physical world behind, digital design can prioritize the tasks computers do best: lightning-fast computation, massive data storage, and absolute reliability. But the loop isn't finished yet. After the processor makes a decision, the user needs a physical response, like hearing an audio alert. To get the data back out, the device uses a digital-to-analog converter, or DAC. It reconstructs those rigid binary codes into a continuous physical output. Immense computing power is only useful if its final output can be physically experienced by the person using the device. Analog and digital integrated circuits function as a single unit. Each domain handles the specific tasks the other cannot perform alone. This complete cycle, capture, translate, process, and reconstruct, is the fundamental architecture of nearly every modern electronic device. Scaling this technology from a single circuit to billions of devices requires a massive industrial infrastructure. This is why Malaysia has focused on building a comprehensive semiconductor ecosystem. It integrates the entire life cycle of the chip, from the specialized design centers where these layouts are mapped, to the advanced manufacturing plants where technicians assemble the final hardware. The ability to navigate the boundary between nature and logic is more than an engineering puzzle. It is the technical foundation for any device that needs to perceive and interact with the physical world.